Hi, happy to introduce our work, ICP-Flow, LiDAR Scene Flow Estimation with ICP by Yanfeng Lin and Hauke Cesar from TU Delft, the Netherlands. First of all, what is scene flow? Given two successful LiDAR scans, our goal is to estimate for each individual point a 3D motion vector. State-of-the-art works are mostly unsupervised, and they predict free-form per-point motion fields. Unfortunately, they ignore the fact that most objects do not deform during motion, the so-called motion rigidity assumption. In this paper, we explicitly incorporate this important assumption into unsupervised flow estimation. Specifically, we represent rigid motion as a single transformation matrix estimated by a classic technique, iterative closest point ICP. In short, our contribution is ICP-Flow, an unsupervised flow estimator which takes into consideration rigid motion assumption. ICP-Flow is fully handcrafted, therefore relying on no deep learning and no training data. Additionally, we consider our predictions as high-quality pseudo-labels for training neural networks. We achieve real-time inference with only marginal performance decrease. Now let's look at technical details. We start with eco-motion compensation, ground removal, and HDB scan clustering. After these steps, we obtain a number of clusters. We then pair these clusters by spatial locality over time. Subsequently, we use ICP to align them and calculate inline ratio and distances. We later reject those unreliable pairs. Finally, we calculate scene flow from those estimated transformation matrices. However, naive ICP does not work in certain scenarios due to poor initialization. In this case, we propose an alternative. Our assumption is that within a short temporal window, objects do not make sharp turns, rotations, leaving translation the only variable to estimate. Since all points from the same objects share the same translation, we can easily identify this shared translation by voting or histograms. We conduct experiments on Waymo, nuisance, and algos using endpoint error and accuracies. We do evaluation on dynamic foreground, static background, respectively. We do 4-point cloud inference without any downsampling. Table 1 shows the results on Waymo. Our results are indicated in the last two lines. As shown in table, our model shows the best performance in terms of both endpoint error and accuracy. The performance gap to the second best is approximately 2 centimeters in terms of EPE. Additionally, we also conduct experiments on longer temporal sequences where time gaps increase from 0.1 to 0.4 seconds. We observe that popular scene flow estimator fail in this case. In contrast, our model are still able to output reasonable predictions, even though the temporal gap increases up to 0.4 seconds. In conclusion, we propose ICP-Flow, an ICP-based scene flow estimator, which takes into consideration rigid motion assumption. We find out that a histogram-based initialization is crucial for ICP. We also consider our pseudo-labels, our prediction as pseudo-labels for training deep neural networks. We achieve not only real-time performance, but also with only marginal performance gap to the best. Thank you for your interest. Our code is publicly available online.